the participants to this workshop. And of course, it is quite a pleasure to receive you and have you all here. Please, the floor is yours, Wolfgang, for your presentation, Solubility Statistics versus Reliable Experiments.
Thank you, Simao, for this kind introduction. And I say good morning, afternoon, and what else for all participants. You see here on the first screen the ions with them we are dealing all the years in the past and also now and in the future. We are working, as Simao said, experimentally and also with modeling. And in the right corner, you see the TERREDA. So we contributed essentially the thermodynamic model to TERREDA to calculate phase equilibrium within these systems of ions except lithium. So, and I thought I will not start with a list of all these guidelines and books about solubility, but I will just quote or take a quotation from Michael Franke from his 20th Rossini lecture, where he said scientific discovery process is defined by never-ending search for the truth of how nature works, and in a significant way, I have some problems here. Okay, now, a significant degree, an ongoing critical evaluation of scientific data. And I added that is also important, the performing of experiments designed to get new data with decreased uncertainty. And in the present days, this maybe also is a quotation from Michael Franke, the never-ending search for truth in the thermodynamics in uncertain era of the internet. Because it gives us possibilities, but it produces also a lot of rubbish. I will speak today about equilibrium solubility, not in a very general, but it's solid liquid equilibrium solubility, not solubility in the meaning, for example, as pharmaceutics when they are trying to get a drug into a soluble form. This is another question. I select 4 examples from the salt systems where I will consider and explain what about uncertainty in these systems and how to deal with these systems in the data evaluation. At first, the system calcium sulfate water. It's well known that it forms 3 different phases, the dihydrate and the anhydrous form and the hemihydrate, with the the minerals gypsum, anhydrite, and basanite. We performed together with Daniela, we made we tried to get more exact information about the transition from gypsum to anhydrite in an aqueous solution. This is a question very important for geochemistry, but also for people dealing with tunnel buildings in rocks. So if you have some anhydrites there, you have to know when it starts to hydrate or the opposite. Why it is difficult to get this temperature exactly? Normally, already from 1900 until now, there's a temperature range discussed between 38 and 62 degrees Celsius. Difficulties consist in the fact that calcium sulfate, hydrous calcium sulfate, does not crystallize really below temperatures of, let's say, 60 degrees Celsius. So you can only dissolve this mineral in an aqueous solution, but crystallize at temperatures. Therefore, it's difficult to cannot observe this transition from gypsum to anhydride directly. And it was the collection from Boris Grumgarz in Journal of Physical and Chemical Reference Data in 2018, who collected his personal collection of data of sulfates of alkaline and alkaline earth metals. And he collected 1 year before also chlorides and bromides of these alkaline and alkaline earth metals. And he collected data from 110 papers for this in the system, starting with 1843. And because of these difficulties to get exact solubility datum for calcium sulfate at a certain temperature, he had to increase the range of data only 80%. If the data were within 80% confidence, he accepts this data. For gypsum, he could set a limit for 94%. So here you see just from his paper, the solubility curves of these three minerals, the semihydrate, which is all the time metastable phase. Blue line is the anhydride, the anhydrous some sulfide, and the green line some solubility curve. The crossing point of these two curves determines the transition from, or the conversion from gypsum to anhydride. So the question is to fix this crossing point as exact as possible. Nearly every second or third years appears a new data evaluation about these solubility curves to fix this transition point, but it's never really finished. So I tried once more to fix this temperature. So I took the data from Grumgarz separately for anhydride and gypsum, and here you see the anhydride solubility curve with some data from his tables, and also with some authors here listed. It's not all, some of them. And I saw this, it turns down at temperatures. This is very unusual for anhydride. And so I looked into the original from Jala, and I saw this was not anhydride, it was gypsum solubility. So, and I looked all these, nearly all these papers for some details. And so we deleted some points, and we had then to a temperature of 100 degrees Celsius, 63 solubility data points. And we made a new fit. You see this black line, this is the new fit for the anhydride solubility. And the change in the area where we are interested, between 40 and 60 degrees Celsius, is very small. It's nearly identical curves. But we see that will have an influence on the crossing point. You see here on the bottom the equations, the quadratic equation describing these 59 points. Yeah, all this data, all this thing, what I'm doing now is published in the Frontiers, in a special issue dealing with solubility in relation to radioactive waste disposal in rocks. So then the gypsum curve. Of course, there are many data between up to 100 degrees Celsius. Gypsum crystallizes also above the stable temperature from aqueous solution. And you see, of course, some spread. All the crosses are the data accepted by Grumgarz, and which gave his fit. And again, we looked into the original data once more, and you see here this is red below, this is red arrow, the data here from Inota, and we saw these are really wrong data, because misinterpret the solid phases. So there are some other points which we had to remove, the black arrows here. And so we ended up with 182 points and fitted this stability data. And this is the black curve. The red one is from Grumgals and the black curve is from our. You could say, okay, nearly the same thing. But if you enlarge the temperature range between the interesting 40 to 60 or 40 to 50 degrees Celsius, you see the effect of this change, of this eliminating of wrong data, or at least not accurate data. The black curves here on the left side, you see this is the anhydride and the gypsum curve fitted by Krumgauss, and the blue gypsum curve and the green anhydride is according to our fit, and the transition, the crossing point, is already shifted about lower temperature. So it's about 44 degrees, and Krumgauss had a fit of nearly 46 degrees. But if we include still the uncertainty range, then this crossing point between the anhydride and the gypsum curve again is in a larger range, which is not sufficiently, it's not satisfying our goal. So then I went once more into the old literature, and we found 4 papers where the authors have actually the focus on this position point, on this crossing between the gypsum and anhydride stability curve. The authors you see here, Hill, Bock, Power, and Pozniak, entirely independent papers. Surprisingly, the crossing point for all these 4 papers are within a very narrow temperature range, nearly 42 plus minus less than 1 degree Celsius. And so I can ask, if we take their data and make a fit for anhydride and make a fit for gypsum again, if we mix this data, then of course uncertainty increases again. But in my opinion, this is the evidence that the transition temperature is really 40 degrees Celsius with a very small uncertainty. These papers are made totally independent. They have also used different analytical techniques. And what is most important with anhydride is the preparation of the anhydride for the solution experiments. They were careful to get an anhydride which has no fines in it, because if fines are dissolved from anhydride, they will never crystallize again. You have not the chance to reach the equilibrium from the supersaturated state. You can only approach the equilibrium from the undersaturated states. And Pozniak made this dissolution experiments up to 1 year equilibration. And so, in my opinion, this is the most important aspect, that they reached such accurate results. And another aspect is they had different analytic techniques, but they used the same technique for the 2 different phases. So individual errors in some kind are compensating because it's the same, nearly the same for both phases. So therefore, I think this is really the transition time we can give. We can write down it's finished, it's 40 degrees Celsius, 42 degrees Celsius, and with a very small uncertainty. And then we got exactly or totally independent evidence that this temperature is correct from the thermochemistry. Already in the 1941, Kelly at the National Institute of Standards in USA, he made measurements of the dissolution enthalpy of gypsum and anhydride and determined the difference of both. And he measured the heat capacity of these both solid phases. For water, all is known exactly. And then you can write down the expression for the energy from the enthalpy and from the entropy determined through the heat capacities. And if this function goes to 0 independence of temperature, then you have the transition temperature. And this was also about 42 degrees Celsius, but with a really large uncertainty. It's too large. And this was because the heat capacity of the phases were not determined accurate enough. And the number of measuring points was not large enough. So this has done Roby in 1989. And so he got a very much smaller range of uncertainty from his measurements, but the same, nearly the same transition temperature. And we looked again into his paper of Kelly. We said the uncertainty, this is uncertainty from these two red lines here, which were given by Roby. But if you look in the solution enthalpy of Kelly, you see he was very, he gave an uncertainty which was much too high. This can be seen from his tabulations. So we see, in our opinion, uncertainty is only 2.8 degrees Celsius. We have quite totally independent evidence that the transition temperature is 42 degrees Celsius from solubility experiments and from thermochemistry. This is quite a nice example how thermochemistry can support solubility experiments, but there are not many examples of such type. This encouraged me to look into another system, sodium chloride water. This, of course, sodium chloride is the most investigated and the simplest salt we know. There are already 3 data compilations. The team of Roger Cohen-Haddad and Lorimer and 13 other members of our subcommittee made this solubility data series volume 47 in 1992. And then the personal collection of quartz published in 2017. And there's a new technical report from 2022 from Ala Basileva. Looking into the solubility series volume 47, you will find 481 experimental data points from 80 authors who considered halide, that means the sodium chloride anhydride or sodium chloride as solid phase. There are also some points with the dihydrate and with ice, but do not consider these. The group accepted 397 points in the temperature range below 110 degrees Celsius with an uncertainty of plus minus 1%, and at higher temperatures 2.5%. 75 points were considered as not accepted. I was looking through these data and were looking for authors who had really the focus to determine the temperature dependence on solubility. And I thought you need at least, such an author should at least have 4 different temperatures investigated. So I found from these 8 authors, 30 have done this with at least 4 data points. And the collection of guides is much larger than 773 data points from more than 300 papers and 200 authors, accepted more points. And so you see that he has in his collection 57 authors not covered by the UPAC collection evaluation. And Ala Basileva once more looked into the collection of Kromgals and added 82 papers from more new papers from the NIST collection of literature. So I ask myself the question, we have the statistic about these all this data. In all these three cases, we have equation for the solubility. You see here up to 200 degrees Celsius. More or less, they agree each other. Vasileva pointed out that IUPAC equation has some problems near 200 degrees Celsius and improved it with the blue line here, and the red line is from Kromgals. So below 100 degrees Celsius, the difference is 0.7%, above at the temperature 2.6%. This could be good enough, but I ask you, for such a simple sort, it should be possible to get more accurate results. Yeah, this is just the same course, but with some show the scatter of the experimental points. The points are more than 1900. So we see no real difference between the old papers and the new one. So, and now directly the deviation plots taken from the paper of Ala Basileva. You see here the UPAC equation and the experimental point have here some bias. So then we see the Kromgals equation from his paper. To higher temperatures, there's some swing in the data. More or less, it's described between 2%, it's minus 2%. In my opinion, it's not accurate enough. And the description of Ala Basileva is well distributed errors, but the error in the low temperature range is 0.7%. In the higher temperature range reaches to 2% approximately. So I was looking for, in all these papers, can I find papers which are very, very accurate? What was the aspects? Of course, the paper should be focused on the temperature dependence of the solubility. And other aspect is which lab or which group these data have been produced, have they enough experience or not, and so on. What do you know about groups already? The other aspect was the aspect of the research. If you are only interested in some technical data or some general course of the solubility, or if it's only a point of the subsystem of some higher component system, you will not investigate it with the same accuracy as if you are interested in the system itself. Another question was, are old data less good than new data? And of course, a careful description of the experiments. What the author considered was important in his determination, what he considered. And I limited myself to a temperature below 350 degrees Celsius. And searching and screening all these papers, I find out that these papers are the best one of all. This is from 1885 and from 1884. Andre Rabenstrauch. Rabenstrauch saw already in the term curve, he was exactly, all these points were exactly on the fitted curve. So, and he made just some points which are important. He made really a critical discussion of all previous papers, not just listing, just he was discussing what are the advantages and disadvantages and why. And he was, of course, one of the first scientists really applying continuously shaking solutions, suspensions, careful control of temperature. He used, and this is very important, very different sodium chloride samples and showed that the experiments with these samples agree with uncertainties below 0.3%. And he described carefully how he sampled the solution and how he, yes, this was what I'm missing in modern literature. And he also controlled the saturation. That means he equilibrated from supersaturation and undersaturation. And what is in modern literature never been done, he made a vacuum correction of all the weighings. That means he considered the buoyancy of the sample. And if you will work with accuracy better than 0.1%, you have to do this. And I'm not sure that modern students even know about it. And he determined the solubility by drying the solution. And he very careful was in drying the samples so that he can really get the sodium chloride without loss, but also without water. And it was the same thing in this paper. So and then I took this data, and you see it here from both papers. They are online. There's only one point, a little bit. This is not much. So better to see here. These two papers with circles and with the crosses in black. This is all between 0.1% plus minus. Red points are the points from Glenn Hafter, who asked himself this question in a conference in 2012. And he stated that he is in agreement with the blue points from the IU-Pack equation. This is the numbers of his citations. And this point, a little bit outside from him, he explained also that there was something wrong. So we can expect from these two papers from 1885 and 1884 that the solubility can be determined to 90 degrees Celsius within 0.1% accuracy. Then I will not show and discuss all these papers and all these plots I have done with the other authors. Just to mention that I excluded statistical considerations. I excluded descriptions of the experiments. And if, for example, in a really outlying point is existent and the author did not explain this why, then I conclude that this is not a very accurate investigation. He was very honest, not accurate. So this was a low temperature range. In the higher temperature range that did up to 350 degrees Celsius, there are not so many papers. And the authors are well known, at least for me. So this, if you look very roughly, they're on a nice line. But in the scatter plot is more than 2% difference. And for every author, I have some arguments why I should take them. Bernhard was only interested in general review, and he had a so-called visual polythermal technique in ampoules and looked when the crystals were dissolved. Then the other technique, Urusova, I know these apparatus, I was measuring with her, Marina Urusova. He was very carefully working, but this apparatus was constructed for very high temperatures, and 350 was the lowest one. So it would not be applied to lower temperatures. Evil itself, he made some kind of volume pressure measurements, and he estimated from this data probability, and he said for himself that it's not very accurate. Really accurate are the measurement of Liu and Lindsay, who measured in the sense of vapor pressures, but also for the saturated solutions, and extrapolated their osmotic coefficient data to the solubility limit. This was very accurate, and I show all these slides I have done with this data. This is really accurate work. So I could take only this point, but this is not good. We need at least an independent second measurement. And so I decided to take Schroeder. There's an E missing. Schroeder, he had an analytical sampling technique. So he sampled from an autoclave the sample and analyzed it. If I take the data from these two authors, from Leo Lindsay and Schroeder, you see this line here. It can be fitted with this equation up to 350 degrees Celsius. And if you look for this scatter plot, you see there are some scatter, but mostly below 1%. And the data of Lindsay are mostly below 0.4 or 3% even. If you take a simpler equation with one parameter less, the scatter is larger, but it really does not describe exactly the data. So I was convinced to have found the four most accurate papers describing solubility of sodium chloride in water up to 350 degrees Celsius. So I took two different equations. The equation for the low temperature range from 0 to about 80 degrees Celsius. This is a black curve here. And the high temperature from 150 to 350 degrees Celsius. Of course, below this temperature, this goes away, but it's astonishing that the measurement up to 80 degrees Celsius, the fit even describes the data up to 250 degrees Celsius. Can be accidentally, but it's also a sign that these data are very, very accurate. So what I have done then, you see here in between 100 and 150 degrees Celsius, these blue points here, or 80, these blue points are scattering. And I decided I take this data and this fit and produce, Michael, as you are also using sometimes, produce the this equation, produced a lot of point here, a lot of beta point here, and then fitted these data points. And this is the result. This is the equation from this fit, where these data are not included in the fit. And you see here this higher scatter. It's better to see here. This is a range between 80 and 150 degrees Celsius. It's really scattering. And this has an experimental reason, of course, because all the methods you are using in the low temperature range are not suited with when you have higher water vapor pressures in temperature above. If you use a method, the ampoule method, the autoclave method, used at a very high temperature, they are not sensitive enough in the low temperature range. So in this temperature range, you have really not good measurements. So this is, I think it was, yeah. As a final picture, I took the thermodynamic model of Archer, which is a model of sodium chloride water system up to 350 degrees Celsius, also considering pressure dependence and so on. So it's a very, very complicated model with, I think, 50 parameters. And he presented in this paper also solubility data. He also used 76 solubility data. And his selection of data is not, it's more or less occasionally. So is with my judgment, also in the high temperature range, the error should be below 1%. But this is not the best you can reach. You also not consider these old papers. So this encouraged me to look in the data selection of Jitka Eiseldorfer, also published in the SDS series, sodium nitrate water. And you see here the plot of the curves from Eiseldorfer. Then there was also from Donald Archer in 2000 dynamic model. It fits quite good. And the scatter is quite large. You see here the scatter plot. It is nearly 4% or at least 3% in the whole temperature range. And the red points are from Mulder. These are from Mulder. This is a book written in Netherlandish language. These data, there are a lot of data there from different sources also, are often cited as experimental data. I read this with a Google translator. I translated the text, and so he made some experiments. These tables people are using are not really experiments, it's just interpolated data. So I stopped this evaluation with the sodium nitrate, invested not so much time here, but I'm convinced that the data will generally be less accurate because of the chemical problems you will get with sodium nitrate decomposition and so on. Then I will come to the last example, the magnesium sulfate water system. And here I consider particularly the kieserite as a mineral phase. Magnesium sulfide forms a series of hydrates, which I have listed here. Sometimes this hydrate is the so-called 5-4 hydrate, which is already known from Van Hoff's time. It's not really a phase. I will explain this later. And I will mention that Michael Steiger made a very extensive thermodynamic model of including this system. So the next slide shows the conclusion of Donald Archer and Joseph Roth from their thermodynamic model of the system magnesium sulfate water. And they concluded that they could not decide what is the right curve. The Kieserite curve, the right curve, you see here the data points. This is essentially one work only from Robson. And the problem is that this Kieserite has negative temperature coefficient with temperature. And very high temperatures is very good, but there's a question of the hydrolysis of the magnesium sulfate in solution maybe formed some kind of basic salt or something like this. And it could influence or decrease the solubility also. In the lower range, the data are scattered. This is just these data I took out as wrong data. I'm sure that they are wrong. And this is the data from collection from Grunwald. It looks quite nice. You have the near 0 degrees Celsius 11 hydrate, then comes the hydrate, you have the hexahydrate curve. Tetrahydrate is in the metastable range, and then the monohydrate, right, is this black curve. With increasing temperature, solubility goes down very strongly to very low temperature, very low solubilities. And you see here, below 100 degrees Celsius, the scatter of the data along this Kieserite curve is quite high. There's also high scatter in the hexahydrate range because this has a tendency to supersaturate very strongly also. The Kieserite coefficient is very important to solve, more accurate, because you see here the transition between the hexahydrate and the monohydrate is about 70 degrees Celsius. in nature we find kieserite as a mineral, particularly in Germany, in the so-called, you see it here, Südharz Unstrut. And it's important for the potash recovery. Potash you can make from this mixture of minerals, sodium chloride, potassium chloride, carnallite. This is so-called carnallite, a mixture of all these minerals with kieserite and anhydrite. This kieserite must have been formed at lower temperature than 70 degrees Celsius. And another very practical question is, if you produce potassium chloride from this mixture here, you produce a lot of magnesium chloride solution, and you have to store it, to put something of the solution into the mines back again, as you can see here. Or if you have a whole mine shaft, it could happen that the solution from the surface comes into the mine and it dissolves all these salts. Preferentially, magnesium chloride has a lot of solubility and dissolves very fast. And the question is, when it stops to dissolve the rock? So it will stop when the magnesium sulfate monohydrate, I mean the kieserite solubility limit has reached. And the question is, you have a lot of dissolution and formation of other minerals, salt, within when dissolving all these when dissolving these minerals, and it's going in the direction of increasing magnesium chloride concentration. And here you see the kieserite field nearly at the end of this dissolution process. We have to handle this multi-component system. In this case, it's a 5-component system. And then in earlier times, it was a lot of different graphic presentations. And now we have computers and use thermodynamic models. But you have to establish such a model, and this model should be reliable. This is the first one, was developed from Harvey Möller and in the 80s, the beginning of 80s, from 1980 to 84. And this is a well-known, the so-called Harvey Möller-Weir model. It represents, in a sense, the experimental data in this multi-component system from Dance, from 1933. And there's a more new compilation of data from Ustovsky and Dieter in the book. And you see it's nearly the same, but not the same. There are differences, and this is all at 25 degrees Celsius. And we have to know this also at 35 degrees Celsius, maybe at 20 or 40 degrees Celsius. It's a quite complex task. And you start to build such a model from starting with, of course, with a simple system, and then go up to the more complicated system. This is these are solubility data known for kieserite, that means monohydrate, in solutions of large concentrations of magnesium chloride. This is a stability range from temperatures of 25 to 75 degrees Celsius. And when you look on these, you cannot really draw curves through these points because they are so scattered. Look, for example, the black are 50 degrees Celsius, the stars, and the circles, the filled circles. So, or you see the 45 degrees Celsius rectangles, green rectangles, and the 40 degrees blue circles. So they are very near, and sometimes the temperature dependence is reversed. So it's not possible to derive solubility constants from such scattered. What is the reason? The kieserite is below 100 degrees Celsius is not crystallizing as kieserite. You see from the PhD work from Ziegenbalg, XRD diffraction pattern, natural kieserite, and this is what you get as a so-called 5-force hydrate, or from a kieserite crystallized from a solution. Even if you are waiting 2 weeks, 1 month, you will have similar diagrams with broadened lines. And the extensive investigations of Siegen bulk, the conclusion was that it's not a phase, but just a distorted phase with some interstitial water. And from all these investigations, he concluded that if you want to synthesize or prepare as a monohydrate, you have to ensure high temperatures and high water pressures. Most of the authors had high pressures or low water pressure or opposite. Or you can just take the 5-force hydrate and make a hydrothermal treatment in a range of 200 degrees Celsius. Or you can boil it in water, just put it into water and evaporate it until the end. Then you get really also a pattern of very near to the natural kieserite. So here in the blue letters, I have once more precise these facts. Dehydration of the hydrate in open atmosphere, as most of the authors are doing, even at high temperatures, will not kieserite similar to the natural kieserite. And from supersaturation, the equilibrium will not reach even at enhanced temperature within 120 hours. Was the limit of the time for in this work. So what we could do, because we wanted also to create a model from the oceanic salt system in order to describe all these equilibria, and we had such a difficult database for kieserite. So we made, of course, some extrapolations of the solubility constant from high temperatures to low temperatures using heat capacity data also, but it's we were not satisfied with this extrapolation. We made such a picture-based model. That means the interactions of the ions in the solution were described by picture parameters and the solubility constants. And so we made the compromise. We documented all this misprint. We documented all these steps of parameter evaluation. And one thing we did, we also fitted the parameters, the mixing parameters in the higher component system. And you see here these lines, these are just the fit of our model stability constant against the data points. So the ideal case, we should have a line along the zero line, but of course you have some slope here you consider. These are these different systems. This is, for example, the magnesium sulfate, sodium magnesium sulfate. You have the yellow here is magnesium chloride sulfate system, and this data we entirely did not take for this. We derived the mixing parameter magnesium chloride sulfate from the higher component system. And of course, this gives then also a better description of the higher component solubilities. So here you see an example of our model. The blue line is the model line. It agrees with the Harvey-Muller model. This was also in presumption we met this time. We should reproduce this model. And you see the experimental data for the higher hydrate, and this is epsomite, the hydrate, and this is vitrified. And you see here, this is the line for the kieserite. And there's one point on it. And Michael Steiger made a very complicated system, a model. This system here, including magnesium chloride, magnesium sulfate system, nearly 15 years later. He had the same diagram you see here. And this is line at 25 degrees Celsius for the kieserite, and we put also this point here. It's very nice. The experimental point is agreeing with both models, and so we could be satisfied, but I'm not. Because you have to look how this was done. You see here the latest experimental points. The green one here is from David Zhang in China. They equilibrated for 10 days, and he stated himself that it was not just monohydrate, there was some more water in the solid phase. And the point from the Polish William Bursa et al. I read this Polish paper using the Google translator, and they made this point by solving anhydrous magnesium sulfate in magnesium chloride solution, and waited maybe until 3 weeks. And I'm saying this is not a real good experiment. We have an occasional agreement between an experimental point and these both models, but it's not a satisfying situation. I did not find any investigations that the author investigated the solution of kieserite in the pure magnesium chloride solution for longer time than 10 days, 20 days maybe, but not more. And the solution kinetics of kieserite is so small, so low in high concentrated magnesium chloride solutions. You have to do this for a longer time. And this is the only possibility to get real solubility data, real data reaching the dissolution limit. So I have some minutes time, yes. Just once more, our model.
Wolfgang, I would say about 5 minutes more.
I'm just
okay.
3 minutes. Once more, our model in the system magnesium chloride, magnesium sulfate. The red line is 25 degrees Celsius and the blue line is at 50 degrees. You see at 50 degrees, the data points are better distributed. The stars, Crystal, sorry, this is your investigation, where I have also made some fit this time. But the focus was here not on the kieserite, the focus was on the tetrahydrite. So we should not take this point too serious. What we see is the 50 degrees Celsius curve and the red curve at 5 degrees Celsius, they are crossing each other, approximately a little bit above 5 mole magnesium chloride per kilogram water. And is it real? Is it really a fact? So this is a more definite calculation with our model, with the radar model. You see here the data from 25 to 70 degrees Celsius. Above a concentration of 5.1 of magnesium chloride, solubility increases for the kieserite, for the monohydrate. Lower concentrations of magnesium chloride, we have what we see in the dilute solution on water. The solubility decreases with increasing temperature. And this is a known fact for salts which have a low solubility. If you dissolve it in high concentrated solutions, the negative temperature coefficient will disappear and will turn to a positive. This is a general feature, but of course, I'm happy that this is reflected in our model. Does not mean that this point of intersection is the right concentration. It could maybe also here or here. I don't know. So I'm coming to some conclusions. I mean, statistical evaluations gives a robust model for the solubility data, but will not reflect the most accurate data. For this, you have really to go into the details in the papers, and the papers must be accurately described or the authors must accurately describe what they have done. They could have done a good experiment. If they have not described all things, then it's lost. The journals really demand for such accurate description, and also the peer reviewers should demand for this. And I have the feeling that in modern times, journals want to have a lot of articles, and so they are cutting a little bit the detailed descriptions of the experiments. Modeling can help interpolate and a little bit also extrapolate missing data, will not substitute accurate missing solubility data. Of course, new tasks require new data evaluations with different focus. The problem how to send these re-evaluations so that easy to it's easy to reflect what is really changed in this evaluation. We should remember that most of the thermodynamic formation data of soluble inorganic compounds are coming from solubility data, and these delta G values cannot be better than the solubility data. And that is also a thing I observed in the last data, I can say, that more and more papers write, we have measured the solubility, but the solubility cannot be measured. It can be determined with a complex process with chemical characterization of equilibrating phases and components. And the author must be aware of the chemistry and also aware of the measuring techniques. This is relevant for the result. I think it should emphasize that one of the advantages of the solubility subcommittee in the IUPAC was that there were some scientists assembling together with different experience in solubility experiments and solubility investigations. And RE stands here for artificial intelligence. Because of this hype, we should not be influenced to this hype. Artificial intelligence will not produce better data, even it will not find data. The only thing it can really help is that it diminishes or overcomes the barriers for language. That means if you have a paper in Chinese, you can read it also as a German. I think I tested this. It is really possible now. So thank you for your attention. Thank you very much.
Thank you, Wolfgang, for your very interesting, comprehensive, and very informative presentation today. It was really very useful and a pleasure to listen and learn with you about the topic on salt solubility. I would now open the floor for discussion and ask some colleagues to present their questions, but first reacting with an applause to the work that Wolfgang did for us today. Thank you very much, Wolfgang.
Thank you.
So, well, if you don't mind, I would like to ask just couple of quick questions and make a couple of statements.
Thank you.
I was involved in that project on IUPAC solubility, and we took a statistical approach because of our very limited resources, but we try to combine our approaches by involving experts who have great experience in particular with these systems, and unfortunately many invitations were declined, and unfortunately we did not contact Wolfgang. Maybe it was our mistake, but we did not know everyone who we could contact. Ultimately, Kirk Nordstrom helped us with his modeling, and so my observation is that unfortunately in many projects people are mostly concerned just to get money and not to maximize output. So we are interested in collaboration, and anyone from this audience who would like to increase the output, we cannot provide additional resources, but we would be happy to collaborate. And one other question. We are trying, one of our projects is just to make some data we have publicly available and involve external models such as Frixie. So just my question to Wolfgang, if I contact you offline by email with a few questions, would you respond?
What do you mean?
I would like to discuss, to ask some questions related to your models, pizza models, Frixie use, and further development and our projects, because we have some data. Actually, we have 9 million data points and 2 million data points in public domain. And we are involved in many projects, but unfortunately, it exceeds our capability significantly. So we are trying to find collaboration. Will you respond if I contact you by email?
Yes, of course. I'm free
Thank
to
you so much.
Yes,
You
no problem.
You know me now. Thank you. Thank you, everyone.
We have approximately, I think it's now 17,000 data points just for the oceanic system.
Sorry, when I mentioned 9 million data points, that's basically organic compounds and mixtures.
Yes,
But a lot of also inorganics, which is out of our focus area. But we have these collections, and we would like to maximize the impact of this and share with colleagues.
Yes, we can discuss this by email first, of course.
And also, I have a kind of comment and question. So, related this project on sodium chloride, I will come back to this. It would be interesting to compare your correlation with what we received. In your presentation, I haven't seen this comparison, but do you have such graphs for the comparison?
Yes, I have it. I have not shown it. So
because I'm just curious because
I have so many graphs.
Okay,
yeah.
if you don't mind,
it's very near because you have seen your model and the IUPAC model and the Grumgals model, and you are very near to the Grumgals equation. And of course, our equation is also very near, but we have a smaller spread of data. Scatter is smaller.
Mm-hmm.
So, but
I'm just curious.
I can, if you're interested, I can send you a plot with your model and with my model.
Okay, please, thank you. And also, what I see in your model, so that my concern was that the SDS equation showed the increase in concentration in the solubility with decrease in temperature at very low temperatures, which our models didn't show.
Yes,
and I believe your model also doesn't show this anomaly.
Yes.
So it was in SDS equation.
Yes, I think our two models are very near. And
okay.
maybe I should mention that Julia Zor, she's also here in the auditorium, and me, we will apply for IUPAC project for an evaluation of the data of the ternary systems in the oceanic salt system. That means we have already the data collection. We have to add some new data, and we are open to have more scientists acting in this project. Maybe Michael, could be interested.
And also I have one quick comment about our IUPAC project. So you mentioned, I completely agree with you that reviewers should be one of the major players in the publication if they see that something is missing in the method description, for example, or characterization description, they should point this out. And currently we prepared, we have an IUPAC project to develop recommendations for reviewers how they should review papers with different experimental measurements. And your expertise in the inorganic solubility measurements, it would be great if you would like to join this project. We will write to you, and so if you agree. So we are preparing checklists for reviewers for different experimental methods, indicating the items they should look into when they are reviewing papers.
Yes, I think I would forward these things also to Daniela Breyer, who is now working in this field in my former groups.
Okay, if you don't mind, I will contact you with this
Yes.
request.
Okay.
Okay. Thank you.
That's a very good output of this project, that you really put your collaborations in a much further positive new views, and in fact it is interesting that we can collaborate and do things that are important, and this idea of having some kind of checking points for people and reviewers to see what they should look at when reviewing papers is quite interesting. And I would like, if I don't see anybody with the raised hands, and I would like to do a more general question to Wolfgang, that is to understand. I possibly it is not that simple to see how it's going to evolve, but after your experience, and you said that you have about 70,000 data points in your database, that is a lot. And what
17.
Oh, 17. Okay, that is a lot too. The thing is to understand, how do you find the accuracy and all the cares doing the experiments? How do people have been evolving from, because you have papers from the 19th century up to now? What is your view over the quality, the accuracy, the methodology, now that we have some much more kind of equipments to do the measurements? How do you see the things today?
Yeah, you ask a very general question.
Yes.
Of course, the first things, as all people are doing, you plot the data first, and you try different plots, different yes, and you read the paper, and also you compare a certain system, and you look for papers of the same author or group of the authors, what they have done in other systems, how this data has behaved. And of course, then you read the description of the experiments. You have your own experience with the experiment. This is very important, and this is what in the solubility data group was important all the time, that people evaluating data should have produced also themselves data. So only in this way you can know what is difficult in producing solubility data for a certain system. And then, of course, yeah, you have to know a little bit about the crystal chemistry, about supersaturation behavior and such things. It's very difficult to answer this very general. And it's very useful to have all these guidelines, how to report from NIST and IUPAC, and also the Journal of Chemical Engineering Data, I think, have such a guideline. You can read this guideline. It just gives you an attention point, but it's not enough to write a paper which is adequate to report about accurate data. And also in our group, not every paper was as accurate as it could be, maybe. For example, we made isopiastic measurements over a longer time at Hans temperatures, and we reached reproducibility around 0.1% in the osmotic coefficient, a little bit better sometimes. But if I read papers about isopiastic determination of osmotic coefficients of a solution, which is the main source for activity data in aqueous system, and the authors write accuracy of 0.01%, and they did not a vacuum correction of the masses they weigh. So this is not exact. Yes. So then you have to look what was the weight difference, and if the weight difference is in the range of 1 gram, then you can say, okay, this is not exactly, the error is at least 0.1%. So, but every report and every property and every system has its own rules, its own things.
Yes,
For
like
example, I'm laughing all the time. In chemical engineering data, it's now uses, and also I think in thermodynamic data, that in the tables and in the footnote you find the pressure in kilopascal or so. This is really a number which is not important. Even the error of the pressure, this is not important for solid liquid equilibrium.
yeah,
But
the
but
fact
they don't write how they have prepared the samples. They don't write really what they have done analytically and so on.
Yeah, because sometimes you look into these big things that you normally should present and not go into the details. And as you said during your presentation, it is really important to go to the original papers and read all is there and
Yes.
try to understand what was the deepness of the analysis. And this is quite the only way for us to understand what is the accuracy and what we can get from the data. So thank you
Yes.
for your answer. There is any other comment or question?
Hi, Professor Wolfgang. I have a question. So my name is John Liu from ORI Systems. So I have a question. The first question is, all of your data collection is above 0 degree. So why didn't you collect data from, below 0 degree C? Because from below, this is SLE equilibrium. So below 0 degree, there's still some solubility data and also different solid phase. The second question is, none of your system have data about pressure dependent. For example, for sodium chloride with water, we have, a lot of pressure dependent solubility data. So the third question is for magnesium sulfate. So all of your hydrate is, for example, monohydrate and TiO11 hydrate. Do you have some data about with non-hydrate, just magnesium sulfate with water, with magnesium sulfate water? The system is early data for magnesium sulfate solid phase? Thank you.
Yes. The first question about the lower temperature below 0. This was not our focus in all these years. I know there's maybe you should ask Michael Steiger. He was more interested in this low temperature research. It was just but in the general, we can say that the low temperature solutions, that means the solubilities and thermodynamic data below 0 degrees Celsius are very bad. For example, if you look for just a simple example for the sodium sulfate, magnesium sulfate water system around 0 degrees Celsius, extremely scattered data. Second question about pressure dependence, this was not our focus. Of course, I know we made an investigation of the pressure dependence of sodium chloride water up to 200 degrees Celsius experimentally, and it was not published really. We ended with the conclusion that it was in agreement with the paper of Pitzer Piper Busse from 1982. So, yeah, of course, the pressure dependence of calcium sulfide is much larger, much more discussed, but this was not our focus. What was the third question?
The third question is magnesium sulfate. Do you have the no hydrate solid phase in the SLE equilibrium?
It has an 11 hydrate, you know.
Do you have a low hydrate, such as just magnesium sulfate?
A lower hydrate?
No hydrate.
No hydrate, I believe.
No. Magnesium sulfate is never crystallizing without water. Never.
I think it's now clear,
Was
isn't it?
this the question?
I think it was the question, yes.
Yes. No, it's impossible because magnesium is hydrating so strong. It's impossible.
So thank you, Jianping, for your participation and interest. Any
Thank you.
Any other comment? Well, I think I will take this opportunity to also tell you that now the page for the new ISSP, the International Symposium on Solubility Phenomena, will be released soon, and I will send the link for you, for all of you that are registered, the link for the next meeting that will be by 12th of September next after summer in Novi Sad. In Serbia. So it's just for you to tell that I received some information, and Madalena, possibly she's also here because we are trying to make and move some of the activities within this workshop to the International Solubility Phenomena Conference. And so I will send you the information already available for you to see the homepage of the conference. So please, some more questions or comments?
So
I
that's
have a
very.
Please, Hala.
I have just one quick comment. So you mentioned about these low uncertainties you mentioned for isopiastic method, and my general comment is reliable authors are not afraid to report real uncertainties. It's very frequent that unreliable authors report so low uncertainty to show that the data are such great have such big good reliability, while it's not true.
No, I say just normally isopiastic measurements are reliable, and they are particularly reliable in more concentrated solutions. But if you measure in more dilute solutions, which is sometimes necessary because you have no other data, then you have to work very, very accurate. And you have, of course, to make a vacuum correction of your weighings. And if you are not doing this, then you cannot measure better than 0.1% accuracy. And this is for dilute solutions, of course, not reliable.
No. I mean different. I'm not talking about just isopiastic method. I'm just general comment about different other all other methods that reliable authors who do the uncertainty budget, full uncertainty budget, are not afraid of reporting the actual uncertainty, which may be big because there are some influential factors. While many authors who do not do the uncertainty full uncertainty estimate. They just report some blind statement about with very low uncertainty.
Yes, yeah. What should I answer to this? I don't know.
No, it's not the answer. It's a comment. It's a comment.
Yes, that's right.
And so
That's
now I
right.
have a quick question to you. Would it be possible to attend that event in September online? Because I'm afraid I will not be able to come.
I
I
believe
have.
well, we'll try the workshop possibly to be online, but the conference will not for sure. I believe
No,
that.
I'm not talking about the conference, about the
But
workshop.
we will try and we all try to see something and prepare something that can be do on site and also online at the same time. But it depends on the technical conditions that Slobodan is going to present there. But we are trying to arrange that. Thank you for the interest, Hala. So thank you also very much again to Professor Wolfgang. It was a really very comprehensive analysis and interesting data. I think that it's quite very evident in these kind of meetings we are doing for 2 years now, is that in fact we all have a responsibility when we are doing revision, when we are doing our own work, to do the things properly and present the things in a good way, because it is the only way to prepare and to publish real important and good information and data. And it is our responsibility to ask our students, our PhD, our master students, to follow these guidelines. And it is quite interesting work that can come from our conversations and our work here. And of course, we will be looking to see what in the future you, Wolfgang, and with the people from NIST are going to do in terms of what are the guidelines for presentation data in solubility of salts. Because it's quite important. It's a very difficult topic, as we could, for those that would not know, could see it today. And thank you very much again for give us this talk that was quite important for us, and thank you for availability on your time. And of course, I'm also thanking all the participants. I will let you know for some other activities in the next future. It is always a pleasure to see you. Let's try to meet some of you, us at least in September in Novi Sad, and in the meantime, we'll be in contact. Thank you very much for your participation. And I don't know if Wolfgang, you want to say anything else, just to say goodbye and a nice weekend for everybody.
Thank you. I would be happy to meet many people, many participants again in Novi Sad.
Yes.
At the conference.
I
have the plan to visit it.
Thank you. It will be very nice to see you there. I also intend to go. Madalena, she's now with us also. She's and we are trying to manage these workshop activities, and we'll give you information in the next weeks. Thank you very much.
Thank you. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Bye. Have a nice weekend.
Thank you.
Thank you. Bye.
Bye all. Take care. Well done, Wolfgang.
Bye-bye.
Bye.
Thank you.
Michael, bist du noch hier?
Michael, possibly Wolfgang. I think Michael already left, but
Okay.
the thing is that, okay, he left. I was confirming that. So thank you
Okay.
again for your time.
Bye-bye.
It was very
Bye-bye.
interesting. Goodbye.